Hi, I'm Chris Pitt and welcome to the third YOU SYNTH development video blog. Today I'm going to be looking at the responsiveness of the percussion pads. That is, how we can make them so they're musical in the way they play. Okay, I've started by trying to come up with some measure of how the electrical signal from the sensor at the bottom of the pad varies with the actual sound coming off the pad, or how hard I've hit it. The first thing I noticed was that it was distorting even when you hit it quite softly. Even if I turn the gain right down, you can see here the little preset sets the gain, so you can set the gain of the amplifier depending on what sort of sensor you're using. However, I found in this case I couldn't turn it down far enough, so I've had to short out resistor 10 there to turn the gain actually down to less than unity. Okay, this is the input circuit. As you can see, it's a simple inverting amplifier. Input resistor of 10k and the feedback resistor of 500k preset and 10k, which gives it a minimum gain of 1, which, as I say, I had to short out R10 here so I could wind the gain down to less than 1. Okay, for the first test I'm recording 2 channels into my trusty audio editor. One channel is the audio recorded through the microphone. The other channel is the audio output from this interface board. Okay, so I'd set it to record and simply go. This gives a series of impulses in both channels of different levels. Okay, so here's one I recorded earlier, and then what I did was I simply zoomed in on one of the impulses and measured the top channel, which is from the transducer, so that's minus 14.9 dB, and I'll just zoom in a bit here. The first big impulse on the microphone, which is a little later, and that's minus 22.6 dB. Then recorded the values on a spreadsheet. This is it here, so that's the transducer output. These are in decibels. The microphone output, and you would expect that these would be proportional to each other. That is, the difference in decibels would always be the same. But interestingly, it isn't. However, the transducer did record a nice spread of decibels, so for now I'm happy with that. Okay, so now we want to see how the signal, the amplified signal from the transducer, which we were measuring here, is treated, is rectified and turned into a nice clean pulse sent out of the output here to be read by the analog to digital converter of the PIC in the Explorer board. So I'm measuring here the amplified analog signal from the transducer, and here the output to the PIC. Doing the same again, recording it into a trusty cool edit program. Series of hits, and straight away we can see we have a problem. The 3 big hits at the end have corresponding pulses out, but the 3 smaller hits here have no output at all. Oh dear. Okay, so a look at the circuit has revealed the reason for this problem, and the reason for the problem is the drop across this diode D2. Essentially what's happening here is that this amplifier is simply amplifying the signal from the transducer. This diode is rectifying it, and this capacitor is smoothing the rectified signal. But since this op-amp is biased to what I've called 2.5 volts, or half the supply, which is 1.6 volts since we're running off 3.3 volt supply, this output, if there's no signal, this output is at 1.66 volts, but this point is at 1.43 volts. Now this is just a differential amplifier with a bit of gain, so it does two things. As I say, it's got a bit of gain, and it adds, and it biases the whole thing, the pulses, to 0 volts. Unfortunately, this input is normally at 1.43 volts, and this input is at 1.66 volts. This means this input has to rise to 1.66 volts, or 200 and some millivolts, before any output appears on the output, before any signal appears on the output. Right, what I propose to do about this I will detail in the next blog.